Yep.
So do you know when I get our exam back, or is there any way we can view it?
Sorry, what is that?
The midterm?
Yeah, the midterm.
What about it? The grade?
Are we going to be getting it back, or?
Oh, I was thinking more like not.
Okay.
we can discuss it.
Yeah.
Did you see the grades in
Yeah,
Canvas? Do you see that?
They did this.
Yeah. I was also seeing them. I was hoping they would be a little bit higher. So I guess it was like the algebra that essentially was the troublemaker there. Just I mean, like computing the numbers. Some of you got it right. Yeah, I just got it back today. Yeah, I think the best would be to do it on an individual basis.
Okay.
So the score that's posted is the raw score. The score that's posted is the raw score.
Yeah. I mean, the number of points would be raw score.
I don't know.
Yeah. Yeah, I was hoping it would be a little bit easier. I guess I sort of underestimated this, like doing on paper examples. So I actually posted homework number 2. Like instead of project, you'll have like a homework. The difference between project and homework, being projects are in MATLAB and homeworks are on paper. So this is like similar, the same structure essentially as the midterm, that you are solving things on paper. I guess if you want to use a calculator, I will not be like policing it. The point is that you don't really have to. And yeah, did you see it already? Is it on Canvas? Can you check? I posted it correctly. Like always to click like 20 times to post one assignment. To like allow online submission, allow file yeah? Okay, so there's like a PDF which is like a thing to practice your determinant foo. Computing determinants for some matrices. And then a little bit of eigenvectors and eigenvalues. Okay. Yeah, so that's for next week. So we'll not do like the standard project. We need to do more of these, I guess. Should be like 50-50 in theory, so I'll see how it goes. The point is that like you might think that like doing things in MATLAB is more practical and you'll be solving some problems in engineering, but like understanding the properties and the theory helps a ton, right? Because if there's like a bug in the code, if you understand the theory, that you know things you can rely on, right? The theory can't be wrong, right? If it's like an orthogonal matrix, then the QTQ must be identity, right? So if it's not, it must be a bug. So it helps you to reason about your code. So it's good to understand it. That's like the justification, the practical justification. Okay, so I still owe you the volume explain the connection between determinant and area or volume. I guess the way you call it in general is measure, like Lebesgue measure, but you have probably never seen that. And I think that would be good for you. So let me just like hand wave the volume. I mean, the idea is clear, right? If we are in 1D on a line, that's just like length, right? If we are in 2D, then we have area. So if my units are meters, this would be meters squared thing. If we are in 3D, we would have volume, so it would be meters cubed, right? And you can imagine we can go to arbitrary dimension with that. Okay, so this is what I finished with the last time, I believe. The big formula for the determinant. I think actually it will be useful for one of the examples in the homework. You will want to recall the big formula and then reason about what does it mean for determinant of block matrices. So the big formula says that the determinant for an arbitrary matrix, and by arbitrary I always mean square and a real matrix, could also be complex, but always has to be square. So it's a sum over all permutations on n-dimensional set. So this means Pn means a set of all permutations of an n-dimensional set. You can just say it's set of numbers 1 to n. There's obviously a total of n factorial, these permutations. So there's n factorial terms in this sum. And this det P is the determinant of the permutation, or the sign of the permutation. The determinant means if I'm looking at the permutation as a matrix, then the det P is like a determinant of a matrix. If I'm looking at the permutation as a mapping, then I can talk about determinant of the matrix of the permutation. In either way, it's just plus or minus 1. It's the sign of the permutation. So it's only saying if I'm adding or subtracting this term. And what the term is, that's important. The term is a product of n numbers taken from the matrix A, from which I'm computing the determinant, and it goes over rows. This is for the first row, second row, and nth row. And in every row, I compute the permutation of that row. So if I have a permutation like this, that means that the first element goes to element number 2. The second element goes to 1. The third element goes to 3, and the fourth element goes to 4. So this is how the permutation permutes my indices, and this is how I index the columns with the permutation. Permutations also form a group. We had the group theory, right? Permutations. Yeah, you have a question?
Can you say the permutations again?
Sorry?
Can you say like the permutation, like how you use the permutations again?
Oh, so yeah, there's like, you can view the permutations like two ways, right? So one way, probably the more basic one, I guess, even if you don't know anything about matrices, you can just reason about permutations as mappings from a set of, from this set to itself, from set of 1 to n to 1 to n. So I was giving this example, so if I have just 3, but one possible permutation is a mapping that maps 1 to 2, 2 to 1, and 3 to 3, right? Or I could have another one, I could have like P1 maps to 3, P2 maps to 2, and P3 maps to 1. But it cannot be this, right? If I said this, that's wrong, right? Because this has to be unique. So every number has to appear once on the left-hand side and exactly once on the right-hand side. That's what captured by this notion that it's bijective mapping. Right? It is saying that it doesn't miss any of the points. So for every point in the target set, I have a point in the input set such that the P maps there, and it's also injective, which means that it cannot be the case that 2 points map on the same one, like here, like 1 mapped on 3 and 2 mapped on 3. So this is not a permutation. It would be a mapping from 1 to n to 1 to n, but would not be a permutation. And permutations, interestingly enough, they form a group too, as we had the group theory stuff. So what do you think is a identity permutation? Yeah, exactly. Just, or even if I look at it as mappings, right? Just Pi is I. I just map it on itself. That's identity, right? And composition of permutations will be another permutation, right? If you look at it as like shuffling of numbers, if I do one shuffling and then do another shuffling, then I just get like a twice shuffling. That's the intuitive way. Or composition of bijections is a bijection. And you can also find for every permutation, you can find an inverse permutation. I guess all you would need to do would be to define it the other way around, right? For this one, I would just say that 3 goes to 1, 2 goes to 2, and 1 goes to 3. So this is my inverse permutation, so they form a group. I don't really want to go into too much details on permutations, but they are sort of cool. They have good, cool algebraic structure because it's a group. They can be, in terms of matrices, they can be represented by permutation matrices. I've been saying this already a few times, I believe. So those are the matrices which are binary square matrices, which have exactly 1, 1 in every row and every column. So look, every row has 1, 1, the rest is zeros, and every column also has 1, 1, the rest is zeros. And the sign of the permutation, that means whether I can get it from identity permutation by an odd or even number of swaps. Swaps meaning swapping 2 elements. So this would be an example where I get it from the identity by just one swap, right? The identity would be 1, 2, 3, and I just swap 2 with 1, so this is one swap. So this permutation would have a negative sign, which corresponds to the determinant of the matrix would be minus 1 of the permutation matrix. Yeah, so I guess this is just like a very brief introduction to permutations. So remember we had like a whole lecture about permutations, but I don't know if you really want to go study permutations all that much. All it really does here in the determinant formula, in the big formula for the determinant, is it picks the sign, determines the sign. So the determinant formula is, these terms are the most important ones, right? This is just multiplication of n terms from the matrix. So they are picked from the matrix. Like on a chessboard, that would be the setting of like the towers that are not, like, how is it called? Not attacking each other. There is probably some better chess term, right? If you have a chessboard and these are like towers, then this would be fine. There is no tower, nothing is in the same row or column, right? Because if they are in the same row and column, then I can just take it. There's better chess terminology, but I don't know that English words. Okay, so are you happy about the big formula? Cool. So what I want to explain now is how determinant relates to area in 2D and volume in 3D. So I don't have a slide, but I have a paper. So let's do the 2D case. Determinant and area. We sort of said it, right? And we said that the units match. That's sort of the first thing to realize, I guess. So let's say that we have. So let's be first in 2D. Or actually, maybe I can make the units argument first. So let's say that I have like 2 or 3 vectors, v1, v2, v3, and I just write them in a matrix, like columns of a matrix. So let's start with just v1 and v2, and let's make a matrix which is just v1 and v2, just 2 columns of that, right? So the determinant of this matrix will be some number, and if I am claiming that this number is the area, has to do something with the area of these 2 vectors, then it should be the case that this will have the right units, right? So what units really mean? Like, units can be arbitrary, right? Like, I am like European, so I would be like measuring in meters, you would be measuring in feet, right? So that doesn't matter, right? What matters is how it changes if I scale things, right? So if I scale the matrix A by T, meaning that I scale each of these vectors by something, then if this is area, then the area has to change by T squared, right? And that's exactly what determinant, if A is a 2 by 2 matrix, does. It will be T squared determinant of A, right? So that means if I scale these vectors twice, then the determinant changes 4 times, right? And this is what we would expect from an area, right? If this is my original area and I scale this twice, then indeed I would expect this to scale 4 times, right? The area. Those are supposed to be the same squares, but that's the idea. And if I have a 3D matrix, if I have v1, v2, v3, then I would like the T go out with cubed, right? Then I do the same thing again. So maybe I could call this A2, which would be like a 2 by 2A. And here I can do A3, where my A3 is just v1, v2, v3. Let me give it the arrow so it's super clear. And the determinant of TA3 will be T cubed determinant of A3, right? Because imagine it if I have like a little cube in 3D, and if I scale each of the sides by 2, then the volume should scale by 8, right? The same way if I scale it down. So this is what I meant, that this is promising. This means that the units work as expected, right? If it wasn't scaling the right way, then I could never claim that this is area or volume, right? But let's do a more concrete example, which I think will make it a little bit clearer. This might have been a little too abstract. So let me pick. So let's do the 2D case. So this is some vector v1 which has coordinates x1 and y1, And here is another vector v2, which has coordinates x2 and y2. Okay. So those are two vectors. So let's take a look. So if I write the matrix A2 and I look at its determinant, then this matrix is just x1, y1 and x2, y2, right? So those are my two vectors. I picked arbitrary two vectors. Here is the origin, here is my 0, right? So what is the determinant of this? You tell me. X2 y1. Yeah, it's a little funny to say, but this is what the determinant is, right? And we can look at it in a funny way. We can look at it as a special type of dot product. We can look at it as a dot product of x1, y1 transpose times y2 and minus x2, right? Because this really is a dot product. So this is the dot product is x1 times y2, that's the first term. The second term is minus x2 y1, right? So I can really write this as a dot product. Everybody agrees? So what is this one is easy, right? That's just my v1 vector. What is this guy? y2 minus x2. That's like something with the v2, right? But something happened to the v2. You know what transformation on the v2 it is? So let's try to look at it this way. If I have some matrix, I'm trying to find out what this transformation is. And the matrix maps x to y2 to y2 and minus x2. What this matrix is? Well, the way I wrote it, it's fairly obvious, right? Yeah?
It's a permutation matrix that you're flipping the sign.
Almost permutation matrix. Because I need the minus here. Yeah. The permutations cannot have the minus in them, right? So this is so let's write it. Let's write it first.
So it'd be
0, 1, and
then
negative 1, 0. Yeah. And again, it's almost a reflection, but not exactly. So when we were talking about rotation matrices, I said that the general form of a rotation matrix is this, right? This was a general R theta 2D rotation matrix, right? And this is exactly a rotation for theta equal what? Minus 90 degrees, I think. So if I put there or minus by half, if you are in radians, because for 90 or minus 90, the cosine will be 0, and the sine of minus 90 is minus 1, so he'll be 1, and he'll have minus 1. So this is exactly rotation by minus 90 degrees. Or in other ways, it's the clockwise rotation by 90 degrees. Like the positive angle means counterclockwise rotation, the negative angle means clockwise rotation. So what this vector y2 minus x2 is, I will call it v2 rot or something. And it means, so this is my y2 and minus x2, and it's somewhere here. So I just took this is my y2 rotated. So I just rotate it by 90 degrees clockwise the v2. So this is my v2 rot. Yeah, and this is the second vector. That's what this question mark is. That's my v2 rotated. So the determinant, and that's interesting, is nothing but a dot product between these two vectors. So what the dot product means, so if I have my v1 t v2 rotated, then we know from the dot product formula that it's the length of V1 times the length of V2 rod, right? Here the rod really doesn't matter, but times the cosine of the angle between the two vectors. So there is an angle between the two. So I'm taking dot product of V1 and V2 rod. I can write it here too. So this is my y2 and minus x2. Okay. So what does this mean? I'm basically here I'm trying to derive the geometric interpretation of the determinant. So the V2 rod times cosine, no sorry, V1 times cosine, that's an interesting thing. That's exactly this side of the triangle. So the V1, the length of V1 times cosine alpha is h, where h is the height. That's why I call it h. The height of this triangle. When I'm looking at this vector V1, like going from V2, so this length here is the h. So this formula is nothing but the length of V2 rod, which is really nothing but the length of V2, right? That's the same thing because this was just rotated, so the length didn't change, times h. So this is the length of V2 times h. And what is the length of V2? Do you copy? What is the length of V2 times h? Well, that's this area of this square, right? Maybe let me make another picture. This was my, actually I will make this longer to make it a little clearer. So this was V1, this was V2. The height was this, and what I just derived here is that the determinant is nothing but the area of this rectangle. Area of this entire thing. And you can see I can do the following trick. I can just cut this rectangle here, this triangle here, and paste it here, right? So it's also area of this parallelogram, right? And now we see what is the geometric interpretation of the determinant. It is the area of the parallelogram generated by the two vectors. Isn't that beautiful? And guess what? If these vectors, if they are getting closer and closer, so if they are getting like this, V1 and V2, they are getting closer and closer, then of course this area is getting smaller and smaller, right? And eventually when they get, so the determinant is getting smaller and smaller, and eventually when they get to the same line, what happens? The determinant is 0 because they are linearly dependent, right? So the matrix is not invertible, and the determinant has, this matrix is singular, determinant has to be 0. So it exactly corresponds to this geometric intuition. Yep.
Right. Is there a relationship between the projection from of V1 onto V2 and the determinant of V1 V2?
What do you mean by projection of V1 onto V2?
Really a orthogonal projection onto the V1 subspace.
Ah. You mean like projection of V1 onto the subspace of V2?
Because when they're totally aligned, then the projection is 1-to-1, you know? 100% of vector V2s can be projected onto V1 and the determinant is 0. Whereas when they're totally perpendicular, then you have the maximum.
Oh, so you are saying just the dot product of V1 and V2, essentially, right? Because that's what's projection of V1 on V2. That's just the dot product of the two. So the determinant is almost exactly that, except that you are taking the rotated V2. Yeah, you have some.
Geometrically, you can imagine changing the angle between V1 and V2 and keeping the same projection onto V2 by extending the length of V1.
Right, you could do that.
So, and there the ratio of the projection to the full V2 isn't going to change, even though the determinant changes.
Okay, and then what?
So I don't think there's a direct relationship. I think if you use the projection and at the angle.
Well, of course, if you'll be scaling one of these, then of course, yeah, you can do pretty much anything there. No, you might be onto something there. All these things are related on some level, certainly. And this is almost like the dot product of V1 and V2, except that the V2 here is rotated this way. And there is actually a reason for that, let me explain that. So first of all, now you have also a very easy formula for computing the area of a triangle, right? Because to compute the area of a triangle, all you need to do is cut it by half, right? So if I want the area of a triangle defined by vectors v1 and v2, it's v1, v2, they define some triangle like this. So if I want the area, I take 1/2 of the absolute value of the determinant of v1, v2. Now I have to take the absolute value because the determinant can also be negative, right? So let's actually clarify that. When do you know when? Let's maybe, yeah, this is like, I guess, the final piece of the puzzle. So maybe that will shed some light on your thoughts too. When it happens that the determinant is negative, you know that determinant easily can be positive or negative, right? It always means the area, but I need to take the absolute value because sometimes I can just get the negative area out of the determinant. So when is it that I get the negative area? Well, that happens if this cosine of the angle will be negative, right? That means if the angle between v1 and the v2 rotated is more than 90 degrees, right? And that turns out that's exactly the case. Let's look at it. If I put the v1 here, and that will be the case exactly when the v2 will be somewhere here. So the v2 will be, for example, here, or here, or here, right? Because what am I doing? I'm doing a rotation. By plus 90 degrees. Wait. No, I did the wrong rotation. I'm doing the clockwise rotation, so I have to do this rotation. Yeah. So if I take this guy and rotate it clockwise, that's the confusing thing. Normally you already counterclockwise. So I get a vector like this. So it will have more than 90 degrees angle with v1, right? And the same thing is true for all of these guys, right? Even this guy that's like almost here, when I rotate it, it's here. So all these, the minus 90 degree rotated versions of v2, they will have an angle with v1 more than 90 degrees. So if the v2 is in this half space from v1, I'm getting a negative determinant. Conversely, if the v2 is here in this half space, then I'm getting a positive determinant. So this is really just the direction I rotate from v1 onto v2. If I rotate counterclockwise in the positive sense, then the determinant is positive. If I rotate clockwise this way or this way, then the determinant is negative. Do you see that? So the sign of the determinant is the relative position of v1 to v2. The sign of the determinant is negative if I get to v2 from v1 by negative rotation, and it's positive if I get from v1 to v2 by a positive rotation. Positive rotation means counterclockwise, negative rotation means clockwise. So this is the significance of the sign of the determinant. So if I take like two triangles like this, one is like v1 and v2, so this guy is going to have positive area, and if I take the same triangle, except that I relabel the vectors and I make this v1 and v2, this one is going to have the same but negative area. Does that make sense? And you can take this to 3D. I will not do all the derivations in 3D because it would take me forever. Look how long I spent just on the 2D case. But what do you think is determinant in 3D? So if I have 3 vectors in 3D from R3, they form like something like this, right? 3 vectors, completely arbitrary, v1, v2, v3. What do you think is going to be the absolute value? Now we know it's a good idea to take the absolute value of this matrix. Any guesses? Should be very easy to guess by now. Yeah?
It's the volume of the...
yeah, how do you describe that? Still parallelogram or something, right? It's like, it's maybe easier to draw it than to... Huh?
Yeah.
Exactly, it's a skewed box. Exactly, slanted box. Yeah. It doesn't even fit on my page. Yes, it's something like that. So again, you can, huh?
Is that a parallel Eigenvalue?
It's just parallel something. But I'm happy that you have a good intuition about it. Yeah, it's like, you could also say that it's huh?
I was saying if there's some name for it.
There's gotta be a name for it, yeah. But what can we say? Maybe we could say just that it's like the unit cube centered here, transformed by arbitrary linear transformation. That keeps the 0 at 0, just transform the arbitrary linear transformation that does it. Right. So if I wanted to get a volume of a tetrahedron, that's, if you will be doing Fis-based, then we will be computing volumes of tetrahedron. So this is like my tetrahedron. I have the 3 vectors are like this, for example. So the volume of a tetrahedron is just 1/6 of the absolute value of the determinant. That's because I can slice the cube into 6 equal-sized, equal-volume tetrahedra. So here you have like one application of the determinant. You can use it to compute the volume of the tetrahedron. Now guess what happens to the sign? When do you think the sign will be positive and when it will be negative? So clearly it has to do something with the orientation of these vectors, right? In which way they go. And it turns out, again, I'm not going to go into too many details, but the sign depends on the handedness of these vectors. If the handedness is the same as the handedness of my world coordinate system, then the determinant will be positive. If the handedness is opposite, then it will be negative. And by handedness, you know the right hand rule, right? Either I have like a right hand rotation, so like if one is like the thumb, then there is either like a positive or negative rotation. There's another way you can think about it. This is actually something what we are doing for research currently. If I have like if I'm doing finite element modeling of some elastic material, what you do, you chop the material into tetrahedra. Those will be the finite elements. And it can be like liver or like a human body or any like elastic material. It can be a piece of rubber. It's chopped into small tetrahedra, and then we formulate elasticity on these tetrahedra. That's how we simulate. And if it happens, and the tetrahedra in the rest pose, that's where we started, they all have the determinant positive. That's how we orient them. And then the thing deforms around. I'm like stretching the liver or something, or deforming a human character. If it happens, then the tetrahedron goes to negative volume. It means that it inverted, right? It's sort of like sort of like the umbrella effect. Like if you have like an umbrella and it like pops the other way around. So like if this vertex, if it like shrinks, goes to 0 volume, and then it goes to negative volume if I keep pulling it down. That's like completely unrealistic deformation if this was an elastic material, right? It can never invert itself. It can never go to like zero volume in the first place, right? Even like all matter is made from some molecules, and you cannot really squish them to nothing. So the negative volume is something you typically want to avoid. But okay, I guess enough rant. We need to go to eigenvalues. That's actually much more important than this business. Unless you have some burning questions on these issues. I actually do. We are trying to figure out how to like avoid these inversions, which is pretty nasty because the determinant already in 2D is quadratic, in 3D it's cubic, and like doing something with cubic inequalities is pretty ugly. But that's not your problem. Your problem now is to understand eigenvalues and eigenvectors. Unless, of course, you have some questions to the previous stuff. Eigenvalues and eigenvectors, those are really basic and super important things. I'm repeating myself, but probably because most of these things are really super important concepts in linear algebra. It's sort of debatable if it's still like linear because the defining relationship is nonlinear. But let's leave the philosophical questions aside. So what is an eigenvalue and an eigenvector? So again, square matrix and this is again defined only for a square matrix, could be easily defined for a complex matrix. And we will actually, this time we will have to go to complex numbers a little bit. But don't worry, it's not that bad. So the point is that the eigenvector is such a vector v, and the eigenvalue is such a number lambda, such that the multiplication by a given matrix A reduces to just scaling the vector. The matrix vector multiplication AV is the same as just scaling the vector by lambda. That's the definition of an eigenvector V and eigenvalue lambda. One important catch, this is trivially true for 0V, right? For 0V, it's just dumb. It's just saying nothing. Because for every 0 vector, this is true, right? So that's not interesting. So we exclude this case because it's not an interesting case at all. So we say that eigenvectors must be non-zero vectors. This was missing here, but it's actually super important. Zero vector cannot be an eigenvector because it's really dumb. It's not saying anything. So this is the defining relation. This is a definition of what is an eigenvector and eigenvalue. And these guys are related. They are like a couple. It's like eigenvector and its corresponding eigenvalue. Now, why I was saying it's debatable if it's still like linear algebra is that we have two unknowns here, right? We are like, if we were solving this, and we will be solving this just in a second, we will be, for a given matrix, we will be trying to find an eigenvector and eigenvalue of that matrix. And by the way, this is a problem that has incredibly many applications. Probably the most lucrative application of that is Google, the PageRank algorithm, right? Idea worth of I don't know how many $1 billion, and it hinges quite a bit on this concept of eigenvalues and eigenvectors, just to get you motivated. Okay. Oh yeah. Well, I was saying that's debatable if it's like still linear algebra because this is actually a non-linear problem, right? Both lambda and v are unknowns, so and they are multiplied here together. So this is like a quadratic problem, really. But whatever, you still need to solve it. So what does this mean geometrically? So like algebraically, now it's clear what it means, right? We just need to essentially convert the matrix multiplication to just multiplication by a scalar. But what does it mean geometrically? So the matrix A is a linear transformation, right? It takes an arbitrary vector and maps it somewhere to another vector, right? So what this means is that I'm looking for such a special vector, such a special direction, that the matrix A maps it onto the same direction, but maybe scaled a little bit. Maybe scaled up or down, but the direction stays. So geometrically, this means this is looking for a direction that the matrix doesn't change. It might scale it or shrink it in that direction, but the direction, the one-dimensional subspace generated by V, it's invariant to the action of the matrix. So like if we look at it as a line passing through origin, the matrix A does not touch the line. That's the geometric interpretation of this. So maybe I could make some simple. Let's consider, what if A was this 2, 0, 0, 2. In this case, any vector is an eigenvector. It's really just like constant times identity, so it's a very simple type of matrix. So in this case, any vector except for 0, because that I don't allow, is an eigenvector with eigenvalue how much? So if I take, for example, vector 1, 0, so I said any vector is eigenvector, so this better be an eigenvector, right? So this I get 2, 0, right? Which is 2 times 1, 0, right? So this is an example of eigenvector, and eigenvalue is 2. And in this case, which is like an extremely simple case, any vector is good. That's gonna be rarely the case. What is the opposite extreme? Let's take a rotation, right? Like before I was taking rotation, let's take rotation by 90 degrees. There is no real eigenvector, fortunately, right? Because the rotation just rotates, let me do an animation. Rotation rotates everything. So it cannot have a direction which maps onto itself. Yeah?
So the only matrices for which eigenvectors exist are ones that are only like moved in a direction and not a rotation.
That's good. So there are some tricks to it, unfortunately. So the first trick is that because the rotation not having eigenvectors is not nice, we actually go to complex eigenvectors and complex eigenvalues. And if we do that, it turns out that every matrix has eigenvectors and eigenvalues.
It represent the rotation in complex number?
Yes, you need to go to complex numbers there. Yeah, other than that, yeah, it's a good point. I should probably know this off the top of my head. When a real matrix has, it's also like, so actually it will be a little bit better to discuss these things when you have a little bit more of the theory, because right now we have defined just one eigenvalue and one eigenvector, but then there are questions like how many eigenvectors and eigenvalues does it have? Sometimes it can happen that for the same eigenvalue you can have like a bunch of eigenvectors. So let's maybe discuss this theory first, and then we can come back to like the conditions when we happen to have real eigenvectors and real eigenvalues. The trick for the rotation matrix that we will have to play not so much later in a little bit is to take complex ones, and that's what's standardly done. You have to consider complex eigenvalues and eigenvectors in general. So how do we find them? So how do we find that they don't exist in the real numbers? So we just take this equation and we rearrange it, right? We rearrange it to this. So don't be, so this is just like putting this on the other side. Don't be confused by this identity matrix. Obviously, I could just write this. You just stick an identity matrix here, right? That's because without the identity matrix, it would not really be semantically correct, because it'd be subtracting matrix from a scalar, which doesn't make sense. So it means scalar times the identity matrix. But this is just like a trivial transformation of this, right? So for if lambda is an eigenvalue corresponding to eigenvector v, that means that this matrix A minus lambda I must have a non-empty null space or non-trivial null space. That means that this matrix must be singular, so that the null space has the dimension at least 1. And now we have the determinant. We have a very simple way testing for singularity. We just take a determinant of this matrix. So this matrix is singular if and only if the determinant is 0 of the A minus lambda I. Right? Follow this. This is like very important derivation in linear algebra. Did you follow this? I guess it's not so difficult, but it's very important. So let me say it one more time. So I am solving for this equation. The thing I didn't mention, v must not be 0, obviously, right? Because we excluded 0 v. For 0 v, this again would be trivially true. So we are looking for a non-zero v, non-trivial solution of this system. And the non-trivial solution exists only if this matrix is singular. Only in this case we have a null space of dimension at least 1, and we can find a non-trivial solution v. And this is the case if and only if the determinant of this matrix is 0, because we know that the determinant is 0 exactly if the matrix is singular. And now, what is the determinant of this? So remember, the matrix A was given. That's the matrix we are analyzing. That's the matrix we are trying to find the eigenvalues and eigenvectors for. What we don't know is the lambda, right? So the cool thing is that now we can forget about the v. We can just look for the eigenvalue, which is like an easier problem, right? We are just looking for one scalar. We need to find one lambda so that this equation will be true. So the only unknown here is the lambda. It's a scalar. And what this equation is, if you think about it, you realize that this is actually nothing but a polynomial in lambda of degree n. It's called a characteristic polynomial of this matrix. So why is it a polynomial? Does anybody have an idea in lambda? So remember, a's are constants, right? A is given to us, so you can like think of it, they are numbers. You had some?
Because of the
Exactly. Because of this big formula, right? That's sort of, I guess, why I started with. So all these a's are constants. The only thing that can happen there is lambda, right? And in the worst case, I have just n lambdas there. So at most, I have lambda to n, right? If I have less lambdas, then I have lambda to lambda 1. 1 lambda, 0 lambda, lambda squared, lambda cubed, a lambda to n minus 1, times some numbers here, right? But either way, it's going to be a polynomial of degree n at most. Or actually exactly degree n. And then now we know how to solve for the eigenvalues, right? All we need to do is find the root of the polynomial, and we will have an eigenvalue. So I have an example, but I don't have the time to go through it. Yeah.
Oh, okay. Never mind. I read it wrong.
Okay.
Okay.
Everybody happy about this? I will do an example next time. You can also see that the polynomial, if we are in the 2x2 case, that would be a quadratic polynomial. It doesn't always have to have a root, right? It just happens that it doesn't intersect the x-axis. No eigenvalues, unfortunately, and no real ones. Complex one there will always be, but I will explain that better next time. Okay. So don't forget about the homework. Actually, one example of the homework is to compute eigenvalues of eigenvectors. Will probably be clearer on Monday how to do that.